So, continuing from the previous example, previous video, we want to find a closed form for fn, right? We know that fn is equal to fn minus 1 plus fn minus 2. But right now, to calculate fn, I need to calculate everything f1 to fn minus 1 to be able to calculate fn. I don't want that. I want some formula that if I put in n, I should be able to find the value, right? The idea is I am going to look for solutions of the form, hunt for solutions of this form. Hunt for solutions of this form. Life would be great if I could find such a solution. Now, this might not exist, but I am going to blindly hope that it does. This is the standard technique. Whenever you're trying to do differential equations and everything, you look for solutions of this form, generally with exponential functions. Okay. In that case, what we get is therefore x to the n is equal to x to the n minus 1 plus x to the n minus 2. Therefore, x to the n minus x to the n minus 1 minus x to the n minus 2 is equal to 0. Therefore, x to the n minus 2 times x squared minus x minus 1 is equal to 0. Right? Now, this means that either x is equal to 0 or x squared minus x minus 1 is equal to 0. So assume x not equal to 0, then x squared minus x minus 1 is equal to 0. Therefore, x is equal to minus 1, so 1 plus minus square root b squared, so 1 squared minus 4a times 1 times c, which is negative 1, all over 2 times 1, right? Which is equal to plus 1 plus minus square root 5 over 2. Okay? And so you can see that both the sequences fn is equal to 1 plus square root of 5 over 2 squared, sorry, not squared, to the n, and fn is equal to 1 minus square root of 5 over 2 to the n. Both of these sequences satisfy the condition that f of n is equal to f of n plus n minus 1 plus f of n minus 2. If I call this condition as star, then both of these conditions, both of these sequences satisfy star, right? But the Fibonacci sequence is not just defined by this only one condition. There's another condition, that f of 0 is equal to 0 and f of 1 is equal to 1, right? Now, if I put 0 as n, none of these give me 0. If I put 1 as n, none of these give me 1. But what you can see is for every a comma b in R, fn is equal to a times 1 plus square root of 5 over 2 plus b times 1 minus square root of 5 over 2 also satisfies star. Okay, so these are not the only solutions. Any linear combination of the terms also satisfies star. And now I can try to find the proper values of a and b. That gives me this. Therefore, 0 is equal to a times, if I put n is equal to 0, 1 plus b times 1, and 1 is equal to, well, this is f of 0, f of 1, which is a times 1 plus square root of 5 over 2 plus b times 1 plus square root of, 1 minus square root of 5 over 2. Now, the first condition implies to me that a is equal to negative b, or another way of saying it is b is equal to negative a. b is equal to negative a. And I can plug that into this, right? So this condition is just basically f1. And so I get 8 times 1 plus square root of 5 over 2 plus negative a times 1 minus square root of 5 over 2 should be equal to 1. So I can pull out a common, and I get 1 plus square root of 5 over 2 minus 1 minus square root of 5 over 2 is equal to 1, which is equal to a times root 5 minus root 5, so plus root 5 over 2 is root 5. And therefore, I get a is equal to 1 over square root of 5, and b is equal to negative 1 over square root of 5. And therefore, fn is equal to 1 over square root of 5, 1 plus root 5 over 2 to the n, minus 1 over root 5, 1 minus root 5 over 2, all to the power n. Okay? And this is what we call closed form. Closed form for Fibonacci. Fibonacci. Okay? Now, I want to show another thing. Okay? That is lemma. For n greater than or equal to 0, n choose 0 plus n minus 1 choose 1 plus n minus 2 choose 2 plus all the way. This is equal to f of n plus 1. Okay? And this seems slightly bizarre the way it's coming up. And one motivation for it is you can see that via the Pascal's triangle. Okay, so 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1. And the Fibonacci sequence turns out is via these lines. So let me draw these lines in maybe green. 1, 1, 2, 3, 5, 7. Oops, not 7. There will be a 1 here. 1. That's going to be part of it. 1, 5, 1, 5, 10, 10, 5, 1, and so on. So this will cut through these. And so if you look at the sum of these lines, that gives you 1, 1, 2, 3, 5, 8. And if you look at this line, the next one's going to be 1. So 1 plus 6 is 7, 5, 12, and 13. And you can see that it is actually doing the sequence. And we know that these terms are the Fibonacci terms. And these terms are my binomial coefficients in the Pascal's triangle, right? So there is some motivation for why it's coming up. Well, the proof is again going to be via induction. Okay, so base case, n is equal to 0. Well, when n is equal to 0, I get 0 choose 0 is equal to f of 1, which is correct because this is equal to 1 and this is equal to 1 too, right? So things are matching up. Let's check for n is equal to 1 just for fun. 1 choose 0 plus did I make a mistake? For n is equal to 1, it would become 1 choose 0 plus 0 choose 1, which is 0. And that should give me f of 2. F of 2 is 1. Ah, right. F of 2 is 1 by my definition. You're right. Okay. Sorry. Plus 0 choose 1 is equal to f of 2, which is also 1. And this is also 1. So things are matching up. My bad. That took me a couple seconds. Right? And I want to show that for the nth term. Right? So I am going to assume induction step. Assume true for n is equal to k. Prove for n is equal to k plus 1. Great. So I am going to assume it is true for n is equal to k, and now I have to prove it for n is equal to k plus 1. N plus 1 choose 0 plus n choose 1 plus n minus 1 choose 2 plus dot 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 is going to be equal to, I want to show what exactly this is, right? And the idea is I will have to use Pascal's identity, right? So what is Pascal's identity? Looking back at our notes, Pascal's identity says n choose k is equal to n minus 1 choose k minus 1 plus n minus 1 choose k, right? And so I get this is going to be n choose 0 because, well, I don't have a k minus 1 for n choose 0 plus n minus 1 choose 0 plus n minus 1 choose 1 plus n minus 2 choose 1 plus n minus 2 choose 2 plus dot dot dot. And now I'm going to rearrange these terms. N choose 0 plus n minus 1 choose 1 plus n minus 2 choose 2 plus dot 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 plus n minus 1 choose 0 plus n minus 1 n minus 2 choose 1 plus dot dot dot. And by my induction hypothesis, the first part, this by my induction hypothesis is equal to f of n plus 1, and this by my induction hypothesis is f of n, right? And so I get that this is equal to f of n plus 1 plus f of n is equal to f of n plus 2, which is f of n plus 1 plus 1. And therefore, by induction, f of n is equal to n choose f of n plus 1 is equal to n choose 0 plus n minus 1 choose 1 plus n minus 2 choose 2 plus dot 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 up to so on, up to 0, because technically most of these are going to be 0 halfway through, right? Okay,